Welcome to this scientific lecture on flexoelectricity and giant electromechanical responses in nanoscale membranes and thin films. Today we'll explore one of the most fascinating phenomena in materials science at the nanoscale. Let's start with the fundamental question: what exactly is flexoelectricity? Flexoelectricity is the coupling between strain gradients and electric polarization in materials. Unlike piezoelectricity, which requires broken inversion symmetry, flexoelectricity is a universal property present in all dielectric materials. This universality is crucial. While piezoelectricity only occurs in non-centrosymmetric crystals, flexoelectricity occurs in any insulating material, including those with inversion symmetry. Now let's understand the fundamental mechanism behind flexoelectricity. Consider a crystal lattice with positive and negative ions arranged in a periodic structure. In the undeformed state with inversion symmetry, there is no net polarization. If we apply uniform strain to this centrosymmetric material, the positive and negative charge centers remain coincident. No net polarization develops. But now consider a strain gradient, such as bending. The top of this bent structure is compressed more than the bottom. This non-uniform deformation breaks the local charge symmetry, creating a net separation between positive and negative charge centers. The flexoelectric polarization, P sub I, is proportional to the strain gradient. Mu ijkl is the fourth-rank flexoelectric tensor, and the derivative of epsilon jk with respect to xl is the strain gradient. Now let me pose an important question. If flexoelectricity is universal, why don't we see large effects in everyday bulk materials? The answer lies in how flexoelectric effects scale with material dimensions. Let me show you the mathematics. The strain gradient is approximately strain divided by the characteristic length scale L. For a given applied stress or deformation, the strain gradient scales inversely with the size. For bending specifically, the strain gradient is proportional to curvature kappa divided by thickness, which scales as 1 over L squared. In a bulk material with thickness of 1 millimeter, strain gradients are extremely small, on the order of 0.001 per micrometer. But in a thin film with thickness of just 10 nanometers, the strain gradient can be 100,000 times larger, around 100 per micrometer. This gives us a giant enhancement factor of 10 to the 5th power. This is why flexoelectricity becomes dominant at the nanoscale. Let's examine specifically how curvature and bending amplify flexoelectric effects in nanomembranes. Consider a bent nanomembrane with thickness T and radius of curvature R. The outer surface experiences tensile strain, while the inner surface experiences compressive strain. The strain epsilon as a function of position y through the thickness is y over r, where y is measured from the neutral plane. The strain gradient through the thickness is simply 1 over r, the reciprocal of the radius of curvature. Therefore, the flexoelectric polarization is proportional to mu times 1 over r. Tighter curvature produces larger polarization. For a radius of curvature of 100 nanometers, we get massive strain gradients of 10 million per meter. This generates enormous polarizations. Let's work through a quantitative example using strontium titanate, a model system for flexoelectricity studies. The flexoelectric coefficient for strontium titanate is approximately 10 to the minus 9 coulombs per meter. Consider a strontium titanate membrane with thickness of 10 nanometers bent to a radius of curvature of 100 nanometers. The polarization is mu times 1 over r, which gives us 0.01 coulombs per meter squared. This is a huge polarization comparable to strong ferroelectrics. The effective electric field is P divided by epsilon naught epsilon r. For strontium titanate with relative permittivity of 300, this gives us approximately 4 megavolts per meter. This enormous field strength is sufficient to switch ferroelectric domains, trigger structural phase transitions, or induce significant electronic property changes. Another important question: what types of materials exhibit the strongest flexoelectric effects? Materials with high dielectric constants tend to show enhanced flexoelectricity. The flexoelectric coefficient often scales with the dielectric susceptibility. Perovskite oxides like barium titanate, strontium titanate, and lead titanate are prime examples with large flexoelectric coefficients. Polymers such as polyvinylidene fluoride also show significant flexoelectric responses, especially in thin film form. Two-dimensional materials like graphene and molybdenum disulfide exhibit flexoelectricity, particularly important given their atomic scale thickness. Let's compare flexoelectricity with the more familiar piezoelectric effect to understand the differences. Piezoelectricity requires non-centrosymmetric crystals, is linear in strain and size independent. Flexoelectricity is universal, linear in strain gradient, and scales inversely with size, becoming dominant at the nanoscale. For bulk materials larger than 1 micrometer, piezoelectric effects typically dominate the electromechanical response. But at the nanoscale below 100 nanometers, flexoelectric effects can exceed piezoelectric contributions by several orders of magnitude. Now let's discuss the exciting applications enabled by flexoelectric effects in nanostructures. Flexoelectric nanogenerators can harvest energy from mechanical vibrations, converting strain gradients directly into electrical power with high efficiency at small scales. Ultrathin flexoelectric sensors achieve giant electromechanical coupling coefficients, enabling detection of minute forces and pressures with exceptional sensitivity. Converse flexoelectricity, where electric fields generate strain gradients, enables nanoscale actuators and artificial muscle applications with precise control. Flexoelectric fields can manipulate domain walls and electronic properties at nanoscale interfaces, opening paths for novel nanoelectronic devices. How do researchers actually measure flexoelectric effects in nanoscale structures? Let me describe the key experimental techniques. Piezo-response force microscopy, a variant of atomic force microscopy, can probe flexoelectric response by measuring electrical signals generated by AFM tip-induced bending. Nanoindentation creates localized strain gradients. Simultaneous measurement of generated charge reveals the flexoelectric coefficient. Suspended membrane samples can be bent in a controlled manner while measuring electrical response, providing direct flexoelectric characterization. Here's a schematic of an AFM-based flexoelectric measurement. The tip applies force creating local bending, generating strain gradients that produce measurable electrical signals through the flexoelectric effect. Let's delve into the theoretical framework used to describe flexoelectricity from first principles. The free energy functional includes 3 key terms: elastic energy proportional to AIJKL, epsilon squared, flexoelectric coupling proportional to μIJKLP times strain gradient, and electric energy proportional to P squared over chi. By minimizing this free energy with respect to polarization, we obtain the equilibrium polarization distribution in the strain system. The resulting polarization is chi mu IJKL times the strain gradient, where chi is the dielectric susceptibility. Notice the effective flexoelectric response scales with dielectric susceptibility. High-permittivity materials naturally exhibit stronger flexoelectricity. An important aspect is understanding where the transition from piezoelectric to flexoelectric dominance occurs. The ratio of flexoelectric to piezoelectric polarization scales as mu over L divided by d times sigma, where d is piezoelectric coefficient and sigma is stress. The critical length scale, where effects are comparable, is L critical approximately mu over d sigma. Below this length, flexoelectricity dominates. For typical perovskite materials with mu around 10 to the minus 9 and piezoelectric d around 100 picocoulombs per Newton, L critical ranges from 10 to 100 nanometers. This critical length scale explains why nanostructures with dimensions below 100 nanometers exhibit fundamentally different electromechanical behavior compared to bulk materials. Flexoelectricity becomes even more interesting under dynamic conditions, especially near mechanical resonances. When a nanobeam or nanomembrane vibrates at its mechanical resonance frequency, the amplitude of vibration is greatly enhanced, creating enormous dynamic strain gradients. This visualization shows a vibrating nanomembrane. The oscillating curvature creates alternating strain gradients, generating an AC voltage through the flexoelectric effect. The dynamic polarization is mu times the dynamic strain gradient, which scales as amplitude times omega squared over L times cosine omega t. The mechanical quality factor Q amplifies the vibration amplitude near resonance, boosting the flexoelectric signal by a factor of Q, which can exceed 1000 in high-quality nanostructures. One experimental challenge is separating flexoelectric contributions from piezoelectric ones, especially in materials that exhibit both effects. The cleanest approach is to use centrosymmetric materials like strontium titanate, which have no piezoelectric effect but do have flexoelectricity. Compare the electromechanical response between bulk samples and nanostructures of the same material. The nanoscale enhancement indicates flexoelectric contribution. Systematically vary the bending curvature and measure how response scales. Flexoelectric contribution should scale as 1 over radius of curvature. We focused on direct flexoelectricity, where strain gradients generate polarization, but the converse effect is equally important. The converse flexoelectric effect describes how electric field gradients can generate mechanical strain in materials. The strain epsilon ij is proportional to the flexoelectric coefficient mu ijkl times the gradient of electric field Ek with respect to xl. This enables voltage-induced bending and shape control of nanostructures, useful for reconfigurable nanodevices and soft robotics at the nanoscale. Here we show the converse effect. An applied electric field gradient induces bending through the converse flexoelectric mechanism, enabling electrically controlled mechanical actuation. Let me highlight some recent breakthroughs and future research directions in flexoelectricity. Recent work has discovered giant flexoelectric coefficients in hafnium oxide-based thin films, exceeding 10 to the minus 8 coulombs per meter, an order of magnitude larger than traditional materials. Researchers are using flexoelectric fields to control electronic and optical properties of two-dimensional materials, enabling strain-tunable devices. Flexoelectricity has been proposed to play a role in biological systems, particularly in cell membrane deformation and neural signal transmission. Flexoelectric effects in bent semiconductor nanostructures create built-in fields that can enhance charge separation in photovoltaic devices. An important theoretical question: what ultimately limits how large the flexoelectric coefficient can be? Thermodynamic stability requires that the free energy remain bounded, which places fundamental limits on the maximum polarization that can develop. Practically, dielectric breakdown sets an upper bound. When flexoelectric fields exceed the breakdown strength, material failure occurs. The maximum polarization is limited by epsilon not epsilon r times breakdown field, typically around 1 coulomb per meter squared for most materials. At extreme strain gradients, lattice instabilities and structural phase transitions may occur before reaching the thermodynamic limit. Based on our understanding, what are the key design principles for maximizing flexoelectric effects? First principle: make structures as thin as possible. Reducing thickness from 100 to 10 nanometers increases strain gradients by a factor of 10. Second, select materials with high dielectric constants, as flexoelectric response scales with dielectric susceptibility. Third, engineer structures with maximum curvature, such as highly bent membranes, wrinkled films, or nanostructured surfaces. Fourth, for dynamic applications, operate near mechanical resonances to amplify strain gradient amplitudes by the quality factor. Let's work through a practical design example for a flexoelectric nanogenerator. Design goal: harvest energy from ambient mechanical vibrations at 100 Hz frequency. Material selection: barium titanate thin film with flexoelectric coefficient 10 to the minus 9 coulombs per meter and relative permittivity 1000. Geometry: cantilever beam 1 micrometer long and 20 nanometers thick, designed to resonate near 100 Hz. The resonance frequency is 1 over 2 pi times square root of k over m, which equals 1 over 2 pi times square root of ei over l cubed over m, approximately 100 Hz for our geometry. The root mean square power output is 1/2 q times v squared times f. With quality factor 100, voltage amplitude 1 volt, we obtain approximately 5 microwatts of power. 5 microwatts is sufficient to power ultra-low power sensors, wireless communication nodes, and implantable medical devices. Understanding flexoelectricity requires multiscale modeling spanning from atomic to continuum scales. At the atomistic level, density functional theory calculations can compute flexoelectric coefficients from first principles by analyzing how atomic polarization responds to strain gradients. At the mesoscale, phase field models incorporate flexoelectric coupling to simulate domain structure evolution under mechanical deformation. At the continuum scale, finite element analysis implements flexoelectric constitutive relations to simulate device-level behavior and optimized designs. Validation across scales is essential. Comparing atomistic predictions with continuum simulations and experimental measurements ensures reliable predictive capability. Let me summarize the key concepts we've covered about flexoelectricity. Flexoelectricity is a universal coupling between strain gradients and electric polarization, present in all dielectric materials regardless of crystal symmetry. Flexoelectric effects scale inversely with characteristic length, becoming giant at nanoscale dimensions below 100 nanometers. Bending and curvature are particularly effective at generating large strain gradients, with gradients scaling as 1 over radius squared. Applications span energy harvesting, ultrasensitive sensing, nanoscale actuation, and control of electronic properties. While negligible in bulk materials, flexoelectricity becomes the dominant electromechanical coupling mechanism in nanoscale structures. Looking forward, what can we expect from flexoelectricity research in the coming years? Continued materials discovery will likely uncover new compounds with record-breaking flexoelectric coefficients, potentially approaching theoretical limits. Integration of flexoelectric elements into commercial microelectromechanical and nanoelectromechanical systems will enable new device functionalities. At the ultimate limit, quantum mechanical effects may modify flexoelectric behavior in atomic scale systems, opening new fundamental physics. Bio-inspired designs mimicking natural flexoelectric phenomena in biological systems may lead to revolutionary soft robotics and bioelectronic interfaces. In conclusion, flexoelectricity represents a fascinating example of how physics fundamentally changes at the nanoscale. The inverse size scaling of strain gradients makes the nanoscale regime qualitatively different from bulk behavior. Unlike piezoelectricity, flexoelectricity is accessible in all dielectric materials, greatly expanding the material space for electromechanical devices. Flexoelectricity sits at the rich interface between mechanics and electrostatics, offering deep fundamental insights and practical applications. As a key enabler for next-generation nanotechnology, flexoelectricity will play an increasingly important role in energy, sensing, computing, and biomedical applications.